Hi, this is Hamza, and my team will present on encoder and decoder models. So what are encoder models? Encoder models essentially convert data such as text and images into a structured numerical representation. Essentially, as the name suggests, it encodes input from one form into another form that machines can understand, that is, numeric representation. But this representation also captures the essential features and the contextual information of the input. So let's say that the input is a sentence, I have a cat. We need to know where each word fits into the entire context of the sentence. And so the encoder models capture them in numerical form. How do encoder models actually work? The first step of the process is tokenization. Tokenization essentially means breaking up the input text into different tokens. Now, each word can be a separate token or each phrase can be a token. That is dependent on the model. The next step is embedding. Embedding is essentially vector representation of the tokens, and the dimensions of the vector are up to the model configuration. Essentially, each dimension of the vector captures some specific attribute of the input. For example, we can describe animals in terms of mammals, reptiles, etc., carnivores, herbivores, how they reproduce, number of legs, etc. And so each dimension captures a separate attribute of the input word. These embeddings result in numerical vectors as described in the previous slide, which are then passed through to the encoder. But first, positional encoding is added to these embeddings. The machine does not know where each word is in terms of order with regards to the sentence. And so this positional encoding module adds positional information to those vector representations. This is where the actual action happens when it comes to the encoder. Self-attention is where the model learns what words to focus on in order to contextualize a specific input word. And this mechanism results in attention scores for each of those words in order to contextualize the entire information. This is where encoders differ from RNNs, which do not have enough memory to contextualize all the input. The output from self-attention is then fed into feed-forward networks, which are neural nets that capture the high-level abstractions and nonlinear relationships between the input words. This process can be parallelized, and so we can have multiple self-attention mechanisms operating at parallel, focusing on different words and the different words of the sentence in order to contextualize a word. This process also involves normalization as part of the mechanics of the encoder model. Now, Iverson will speak to the applications of
Hi, I'm Iverson. So I will be talking about the applications of encoder models today. Encoder models are everywhere in the tech we use every day. In natural language processing, models like BERT help systems to understand text context, powering chatbots, search engines, and predictive text on your phone. In computer vision, encoders model like ResNet break down images into key features. This enables facial recognition, object detection, and even automatic photo tagging. They're also essential in recommendation system. Think about Netflix and Amazon. Encoder models analyze your behavior and suggest content that matches your preferences, making recommendations feel personalized. Finally, encoder models play a big role in data compression. Autoencoders condense complex data into simpler forms, making it easier to detect anomalies in fields like fraud detection or medical diagnostics. In short, encoder models help power everything from understanding language to identify images and personalizing your online experiences.
So hi guys, so we have seen how the encoder models works and what are the applications, coming into the encoder models. So now we are going to see how the decoder models works. So two types of, I'm going to explain it in the, what are the decoder models, decoder only models, and what are how it's like able to transform into encoder and decoder transformers models. So I'm going to explain about decoder models, how it works. So as my friend says, like encoder models, like it simply translate into the vectors format, whatever the text comes into the format. So apart from it, like what decoder does is it tries to predict the next token. So whenever the input is given, the prompt is given, so it tries to give the probability of the next token using the pre-trained data set the model has been trained. So what are the defects of this model? So it doesn't capture the new features. So unlike an encoder model, it doesn't capture the features of the prompt or features of the text which you have been giving. So that might be a drawback in this model. So coming into depth of this model, like you can see that we will talk about more about the encoder and decoder models, like how the system design has been designed. So we have talked about the encoder only models, which doesn't have the ability to get the context of the prompt. So what we are going to do is we will be linking those into the encoder models. So when we give the input to the encoder models, it gets into vectorized format, so embedded, and then we will extract the feature from it. So from the feature, we will be giving into the multi-ed attentions and the norms and the CNN models, and then we will be extracting towards the softmax functions. So it will be like reducing the complex multidimensional matrices into a simple probability functions. So from that, we will get the probability of the next tokens which you've been getting out. So you can see, like, I swam across the river to get into the other bank. So yeah, the bank is not the bank, and the river. So river consists of like different meaning. So here the bank and river should maintain the context. So what we are doing is we are trying to embed all the other words into into the context of the single word. So you can see again the part of the piece of the program which we run. So here the predictor sentence for basically we gave for breakfast what I ate. So here you can see like meals, eggs, states, and vitamins, and then drink. So each one has the sorts of probability. So this is what the output of the decoder model gives. So gives the probability, and of the next token, the sentence has to be completed. So this is a short form of the decoder models. Now my friends will be explaining about the application formats. Yeah.
Hi, I'm Harrison, and today I'll be walking you guys through some exciting real applications of decoder-only models. These models are designed to generate sequences, whether it's text, code, or speech, by predicting the next element in a sequence, and they play a vital role in AI systems that we use every day. First, let's take a look at text generations. Basically, ChatGPT models, specifically GPT-4, they're really at the core of AI chatbots like ONQ, which generate human-like text responses. And the decoder-only architecture really helps predict most relevant and contextually appropriate next word in a conversation. And these really makes these models ideal for applications in customer service, virtual assistants, and even in generating creative contents like blog posts or social media captions. And next is code generations. GitHub Copilot, super great example of how decoder models can assist developers by predicting code snippets based on partial inputs, allowing it to suggest entire functions or complete sections of the code. So by automating these repetitive tasks, it helps developers to work faster and focus on those strategic and more complex challenges. And finally, we got speech synthesis. Basically, Google's Tekkatron, it leveraged decoders models to transform written text into natural sounding speeches. And this technology is really vital for creating virtual assistants like Google Assistants, as well as accessibility tools like iPhone screen readers, helping user interact with technology more naturally. It's also being used in content creation like audiobooks, podcasts, and voiceovers in video production. So just as a big or high-level summary, these models really power a range of tools that enhance productivity, improve accessibilities, and enabling more natural interactions with the AI-driven systems. Thanks.
Now let's talk about how encoder-decoder architects work and how it's applied to real-world problems. So encoder-decoder architects can handle inputs and outputs that both consist of variable length sequences and thus are suitable for sequence-to-sequence problems, such as machine translation. The encoder takes a variable length sequence as input and transforms it into a state with a fixed shape. And the decoder maps the encoded state of a fixed shape to a variable length sequence. And one common example is machine translation. In this case, the encoder reads a sentence in one language, such as English, and transforms it into a compressed format or vector that captures the meaning of sentence. And the decoder then takes that vector and reconstructs it into a sentence into another language, like Spanish. And this is exactly how apps like Google Translate work. And another great example is chatbots, like Siri, Alexa, or Google Assistant. When you ask a question, The encoder processes and understands your input. The decoder then generates a response based on the processed information. Now you can also see encoder-decoder models work in text summarization used by tools like Google News or Flipboard, where the encoder reads a long article and the decoder generates a concise summary. So along with encoder-only models and decoder-only models, these models enable tasks like email spam filters, text predictions, and machine translations, etc., in various real-world applications to improve our work efficiency and to enter a new era of AI. Thank you.